Back everyone. So we'll continue talking about this problem of addressing of graphs that we discussed in the last part. So let me remind you what we are doing. So we have this graph with vertex set V and edge set E, and we want a function from the vertex set to the words of length, some length m over the alphabet 0, 1 star, such that the distance in the graph between x and y equals the number of positions j where if one of the words has a 0 and the other one has a 1. Okay, and got number. So we showed that this can always be found. We showed that this function, the existence of such function, is equivalent to a decomposition. There is a decomposition of the edge set of the distance multigraph of gamma into this Biclique, complete bipartite subgraphs. Now, is there always a decomposition of d of gamma into Bicliques? So this question is equivalent to this one. Yeah, how can you do it? Edges, every edge is a Biclique, so you can always do it. So then, with this in mind, this parameter n of gamma is, which is the minimum m, with these properties, this is well defined. Okay, and we showed that this result that n of complete graph Kn equals n minus 1, and upper bound by a construction, lower bound by a linear algebraic argument. Okay, so again, the question here, this is open. N of gamma, I believe it's NP hard to calculate, but we don't know. Okay. So with that in mind, I think someone asked at the end of the previous lecture, what do you know about this n of gamma? So in the original paper, so I wrote earlier at the bottom, let me write it again here. So in their work in the 70s, Graham and Pollack proved for any graph, but so if gamma is connected with diameter d, then this parameter n of gamma is less than or equal, let me write it this way so that people won't get confused about functions, n minus 1 times d. So that way it's clear that it's a product, okay? And I mentioned Graham later on, he made a conjecture, and this is also known as the squashed cube conjecture, that n of gamma is less than or equal than n minus 1. N minus 1 is the number of vertices, okay? And this was proved by Winkler in 1980s. This is a paper in Combinatorica, which is called Proof of the Squash Cube Conjecture, and so he proved that n of gamma is less than or equal to n minus 1. Okay? So for any graph is at most n minus 1. That doesn't make it efficient to calculate because n can be any numbers there and so on. And if you want, so you can find the paper, the original paper is like 3 pages or 4 pages, and if you like a little bit like if you like this type of algorithm, like breadth first search, depth first search, and so on, the way he finds an addressing with n minus 1, length n minus 1, uses this type of algorithms about depth first search, breadth first search, and so on. And you can find this proof also. There is this beautiful book called A Course in Combinatorics by Van Lint and Wilson, and the proof here, this proof is, I think, chapter 10 or chapter 9, something like this. It's half of that chapter. They explain it there, how the proof works. So, yeah. Okay. So this parameter is always the most n minus 1, but for many graphs, we don't know what it is. So let me tell you how the main, so for this parameter n of gamma, if you want to prove an upper bound, so an upper bound, let's say this is at most, I don't know, let's say capital M, what you need is you need a construction. You need to tell me how to put these addresses and so on. So this needs a construction. Now, on the other hand, if you want to prove this is greater or equal, or let's say this is strictly greater than some number, let me call it L, you need to do something like we did for the Tverberg proof, where we said, I want to prove that n of kn is greater or equal to n minus 1. Therefore, I want to prove that, you know, it's, you need to give a proof, essentially. So here you need some kind of proof. Okay, or lower bound. Now, again, for construction, this will depend for each problem. There will be different construction for each problem. But for the lower bound, the main tool for lower bound is the following theorem. You have the graph as before. Now, let's do this example that we had earlier with, I forget which way I did the diagonal and which way I labeled things. Let's say 1, 2, 3, 4. Okay, let's say this one was. Could have been the diagonal the other way around. But this is my gamma. From here, I have the distance multigraph of gamma. Where I have edges, I keep the same. And here I put 2. And from here, I can also create, I mean, I could do it from here directly, but you can also have the distance matrix of gamma, which is, I call D, and you have the vertices 1, 2, 3, 4, and you have here 1, 2, 3, 4, and in the entry xy, you put the distance between x and y. So it would be kind of like an adjacency matrix of this. So you have 0, 0, 0, 0, 1 and 2, 1, 1, 1, 1, 1, 1. The only one that's 2 is 2 and 4. So 2 and 4, and then 1, 1, 1. Okay? So that's the distance matrix. So the theorem here says that for any graph, n of gamma is going to be greater or equal than the maximum of the number of positive eigenvalues of this matrix D and the number of negative eigenvalues of this matrix D. So this is a place where eigenvalues come into play, and they're not eigenvalues of the adjacency matrix. They're eigenvalues of this distance matrix. And so where n plus of D is the number of positive eigenvalues, of D, and n minus of D is the number of D. So before I give you the proof of this result, let me show you how this implies this thing about that we did earlier about the complete graph. So earlier so for the complete graph Kn, what is the distance multigraph of Kn? It's the same as the graph Kn. So that implies that the distance matrix of Kn is the same as the adjacency matrix of Kn, which is Jn minus In. Now for here, what is the number of positive and what is the number of negative eigenvalues? 1 and n minus 1, because this is minus 1 with large multiplicity. So therefore, the maximum of them is n minus 1, and then you plug it into there, you get greater or equal to n minus 1, you're done. Because that's the bound that we did with a linear system of equations. But this is more general because this one you can apply it for any graph you want. Any graph, you just go to the distance and it will get you a lower bound. Okay. So let me give you the proof of this result. So let's say, so assume n of gamma is m. Okay. And so what do we have? Because n of gamma is m, we have this addressing, and what it means, we have this, so we have a decomposition of this distance multigraph of gamma into m of these bicliques. Some of you ask, okay, what's so special? What happens now with these bicliques? But I'll show you in a second right now. x1, y1, xm, ym. Okay, so we have decomposition. So again, this is the key thing. Decomposition partition, it will come back to some equality between a matrix and a sum of matrices. Okay? Now, here, this D of gamma, the matrix that corresponds to it is the distance matrix. Okay? Now, if you have a biclique, how does the adjacent, a biclique looks something like this. You have some vertices here, you have some vertices here, you take all the edges here. In the graph, you could have edges inside here, doesn't matter, but you don't take them in your biclique, and you could have edges inside here as well. This is your xj, and this is your yj. Okay? So this is how the picture looks from the perspective of the graphs. From the perspective of matrices, how does the adjacency matrix of this graph look like? Now, without loss of generality, let's assume the xj come first, then the yj come second, and then I'll give you a formula in a second. So this will look like the adjacency matrix of this biclique between xj and yj will look something like this. A big block of 0, and then here you'll have all one matrix. This is, let's say, xj. Let's say I have vertices here. Then this is yj, and this is the rest. Then here, so you have like 3 blocks like this, 0, 0, j, 0. Here you have the j, but is a transpose of this one. You have 0. And then what else? You will have 0, 0, 0, something like this. Because you don't take any of these edges. You take the vertices, but you don't take the edges, okay? Now, what rank does this matrix have? 2. So, and how can I write it in terms of the characteristic vectors of this subset xj and yj? So the characteristic vector, we talked about them when we talked about vector partition and interlacing. Let me call uxj the characteristic vector. So maybe uj, so that it's easier. Uj is the characteristic vector of xj, and vj the characteristic vector of yj. And this one, for me, all the vectors are columns. So these are n rows 1, okay? So this matrix is rank 2. How can I write it in terms of the characteristic vectors of uj and vj? So think about it like if I take my uj like this, let's say I have, let me see, I'll put it, I'll put it here. So this is uj. So I have 1, 1, 1, where xj is, and I have 0 everywhere else. Okay. And then if I have, yes, and then if I have here 0, 0, 0, this is yj, 1, and then 0, 0, 0. So if I multiply this column vector with this row vector, what do I get from this? Do I get this matrix or I get some parts of it? I get this, I catch this block and 0 everything else, okay? So the adjacency matrix of this will be uj multiplied by vj transpose plus vj multiplied by uj transpose. This is a rank 1 matrix, like we'll catch just this part and 0 everywhere, and this is the other rank 1 matrix which is here, and it will catch everything else. Okay? So you can do that. So now the fact that I have a decomposition means I can write like a matrix equation between the distance matrix and these vectors, and this, these vectors. So let me see where I can, let me erase here, so I'll write it here. Decomposition into xm, this means that D will equal summation from j equals 1 to m uj vj transpose plus vj uj transpose. Okay? So now from here I could get an easy bound for m, lower bound for m, just applying rank to everything. So I can say rank of D equals the rank of the sum, and the rank of the sum is going to be less than or equal than the sum of the ranks, and for each of these terms I will get a 2. So if I apply rank, just by using rank, I get that rank of D is less than or equal than 2m, so I get m greater or equal to rank of D over 2. But as you see, for complete graphs, that's not good enough. That will give me n over 2. And the plus and minus stuff is better. So you have to do some trickery here to get a better bound than rank of, because what is rank of D in terms of m plus and n minus? Eh? The sum of them. And I'm saying I don't want their average. My lower bound is gonna be the bigger of them. So this is a better bound than that. So we have to do a bit of work, okay? So that's the equation. And now how do we interpret it? Okay, so let's consider the following subspace. So consider, let's call it U, which is the span of these vectors U1, blah, 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 UM. But I'll take the orthogonal complement of it. Okay, we'll see in a second why it works. Okay, so this is a subspace in a big space Rn. And let's see what's so special about this space. What's the reason why I picked something here? So, well, let me call it W for now. So take a vector W in W. Okay? Then what happens? W will be perpendicular on each of these U1, U2, UM. Then W transpose Uj will equal Uj transpose W will equal 0 for J from 1 to M. Okay? So now, let's see what can we say about W transpose dW. So I will replace D by this, and so this will be a summation from J equals 1 to M of W transpose Uj Vj transpose W plus W transpose V J U J transpose W. So now, when W meets a UJ, it vanishes. So this part here is here, and is going to be a 0. And when UJ transpose meets a W, it also vanishes. So this part here, it's here, and it's also 0. So this guarantees that yours, this sum will be 0. Okay. All right, so W in here means this happens, that W transpose dW is 0. So why is that important? Well, that implies that W is not an element in the what I call E plus, which is the vector space, the subspace spanned by all eigenvectors corresponding to positive eigenvalues of D. So this is the subspace spanned by eigenvectors corresponding to positive eigenvalues of D. And it also implies the same thing by W does not belong to E minus, which is so here we have to think a little bit, but here's the, I can put here again to save my thing, exercise number 79, no? 28? No. 28? Okay, something. 29. Okay, thank you. So why is this happening? So if you are in E plus, you will be a linear combination of eigenvector of positive eigenvalues, and you take an orthonormal basis and so on. So you take a linear combination of those eigenvectors. When you go into to calculate W transpose dW, remember the calculations we did for the Rayleigh quotients. What came out there? You get with some kind of coefficients, squares, multiplied by eigenvalues, it's a summation of that form. Now, because you take a vector that is non-zero here, some of your coefficients, at least one coefficient is going to be non-zero, so the square of it will be positive, and because your linear combination corresponding to positive eigenvalues, all the eigenvalues that are in that linear combination will be positive. So when you calculate, essentially what I'm saying is that if you take W in E plus and W is not the zero vector, this implies that W transpose dW has to be positive. That's exercise 30, which is the same as exercise 29. So that's basically how you solve exercise 29. Okay. And the same thing here for all negative things. For the negative things, you will be strictly less than 0. Okay, the same problem. So now, how do you wrap this up? The way you wrap it up, you say, okay, so in this space, in Rn, I have W here, and I will have E plus here, and they intersect, this is 0. So other than that, they don't have any intersection, okay? And so what you'll get is that the dimension of W, so because W intersect E plus is just a 0 vector, which comes from there, we get that the dimension, that n is greater or equal than the dimension of W plus dimension of E plus. Now, what is the dimension of W? So W is this thing. So here is a span of m vectors. So inside I have dimension at most m or less. So if you take the perp, you get that dimension of W is greater or equal than n minus m. And you know that you will have equality if and only if those u1, um are linearly independent. So then here you will get at least n minus m plus, what's the dimension of this E plus? N plus. N plus. N greater or equal than n minus m plus blah, blah, blah. You move the m to the other side, so you get m is greater or equal than n plus. And that's exactly what we need. And you can do it the same thing for n minus. Okay?
So for any tree, the n number is going to be n.
For any tree, what? I think n minus, n plus will be 1 and n minus 1 will be n minus 1. I think, yeah. So, yeah. So, in their paper, Graham and Pollack showed also for any tree, n of gamma equals n minus 1. And for trees, I think n plus is 1 and n minus 1 is n minus 1. And then you have to figure out for trees how you do the addressing. But the trees have this very recursive structure. You have the leaf and so on, so you can do like you can address it in various ways. But in general, like I said, this parameter, if you come up with a graph, the lucky situation, which is like complete graph, for example, is a lucky situation where the construction you have gives you the same bound as this eigenvalue, and then you can say this is my number. But there are many cases in which this doesn't happen. So in many cases, you have a lower bound from here, and it's very difficult to increase the lower bound. So let me give you some examples. Can I erase here? Is it okay? Okay. Okay. Let me give you some examples. So for example, for a Peterson graph, if you want to address it, if you get, you have to calculate. We did in the adjacency matrix, we calculated 3, 1, minus 2, 1, 5, and 4. You have to calculate the adjacency matrix of this D. Okay, so exercise 30, calculate it. And what you get from there is that the number of positive and negative eigenvalues, this greater or equal than max of n plus and n minus, I think you get a 5. But this was studied in a paper by Gregory van der Meulen, and there's one more author whose name escapes me, which is called an addressing of Peterson graph, and they could find a construction with 6. But then what they did in this paper, which I'm not going to put you through today, is they analyzed the equality case in this theorem, and they showed that equality cannot happen. If you have equality, they concluded that the Bicliques that you use have to be very large, and then they exceeded the number of edges that you had in the graph. So you could do from here, you could push it. They pushed it by 1 more, so you can do that relatively easy just by going through this analysis. And then, and even for Peterson to get this number is a bit of work, but this is 6. Okay. We have some paper, a paper with an undergraduate student and some co-authors, in which we did we did other graphs. We calculated this parameter for other graphs, something called Hamming graphs. So Hamming graph H, let's say N2, we saw it already. We saw H32 earlier. The Hamming graph is you have n vertices in each row, and then you have n rows, and you have n columns, and everything. Everything in the same row and the same column is adjacent. So, each of these rows is not a path; it's a complete graph, and each of these columns is not a path; it's a complete graph. So for these graphs, we can address them, and we can address more general graphs. You can prove that this addressing for H and 2 is something like 2 times n minus 1. Yeah, so you need that many symbols for this. So this is an n squared graph. So the Winkler thing is at most n squared minus 1, but you can do it with this. This is optimal. This is the exact value. Okay. Now, if you want to play around with this problem, we did a follow-up paper of follow-up work. So, and this is maybe useful because I think we have some code in the, like if you're interested in doing computations and so on, we have some code in that paper. This is a paper, I forget the year, but it's in experimental mathematics. So it's something called addressing Johnson graphs, odd cycles, and random graphs. And this is a paper with Alon, myself, undergraduate student at the time, Brandon Gilbert, Jacques Coulon, and Brendan Mackay. So in this paper, we look at a variety of graphs, including these graphs, which are Johnson graphs. So what is a Johnson graph? So Johnson graph J and let's say D. The vertices are all the D subsets of a set with n elements. So 1, 2, 3 up to n. We can write them like this, n, d. I write this as n between square brackets. This is the notation, yeah. And the edges, you have some set S is adjacent to some set T if and only if S and T intersection is D minus 1. You just take one element out from one and you put something else in it. Okay, so for example, Johnson graph JN1, I know it's late afternoon, you had your ice cream and so on, so you're half asleep, but let me wake you up with a question. Johnson N1, the elements are one subsets of a set with n elements, 2 of them are adjacent if and only if they're disjoint. So, Kn, very good. Okay, Johnson N2, he has a different name. It's a complement of the Kneise graph, but it's something in terms of the complete graph Kn. The vertices are all the 2 subsets. It's the line graph of K. So in particular, Johnson 5,2, this is the complement of the Peterson graph. So in this paper, so Brendan Gilbert, he came up with an algorithm to address these Johnson graphs, and we could prove something that the addressing is at most d times n minus d. Now, bear in mind that these Johnson graphs, the number of vertices is n choose d. So that's very large compared to. And for the longest time, we thought, I mean, his addressing is fairly complicated. We give the algorithm is done in the paper, and you can check it out. And we proved that it's correct, it works. But then we thought, okay, this works, but there is example of NJ63 where this actually, Brendan Mackay did a computation and it found out that it's 8. This thing would tell us upper bound 9, but it's not. So this is not sharp, but it's still open, like what is this value? The other thing that appears in this paper that may be of interest for you is that, you know, like Winkler proved that n of gamma is at most n minus 1. And later on, there was in one of the papers of Ron Graham, he mentioned something that you would be tempted to conjecture that most graphs of gamma, this parameter is n minus 1. Well, we actually proved that that's not the case. So in this paper, we proved that for almost all graphs on n vertices, this parameter n of gamma is at most n minus something 2 plus little o of 1 log of n. So this started as a first, that's why it's important for you to master both theoretical things and computational things. So with Brendan, I asked him, okay, let's calculate for graphs. You can get graphs to 10 vertices and so on, 9, 10 from using this naughty program written by Brendan Mackay. And he ran his algorithm to them, and we saw the numbers. So when you look at the numbers, it didn't look like these ones were most of the graphs. They were actually fewer. So then I talked about this with Noga alone, and he gave this example using random graphs that for most of the graphs, this value is at most this much. And the best lower bound here is something like n over 2, like in terms of eigenvalues and so on. So it's not known what this value will be for most graphs. So this is I think it's a difficult question. Yeah, let me tell you now which one is the hardest graph to actually, for which to find this addressing. And it's actually a very, it's a very easy graph to describe, but it's difficult to, nobody knows. So this is an open problem. And this is, you can find there is a paper by Alan Hoffman in 2001. It's called On a Problem of Zaks. And Zaks studied a related problem in geometry. I'm not going to send you there. But what Alan Hoffman looked at is this graph. You have, we met this graph before. You take a complete graph and you just remove a perfect matching. Okay? So this is a cocktail party graph with 8 vertices. The cocktail party, well, you know, or you can say, yeah. So you have four couples, and nobody wants to talk with their significant other. So that's why you have a perfect matching there. And so for this graph, in general, for this cocktail party graph, let's say of 2m vertices, there is a construction that gives you something like 3m over 2, and this depends on their 3m over 2 plus something depending if m is even or m is odd. There is some construction, which I believe it should be optimal, some recursive construction, you can get at most 3m over 2. Here, lower bound, by using this eigenvalue bound that I showed you with n plus and n minus, this was m plus 1. This is what Zaks did, I think, in the 1980s. That was the best lower bound. So 3m over 2 plus something m plus 1. And then Hoffman, in this paper, I think it's 2001, he make this he added something like something, but it still doesn't reach here. So this is the best improvement of the lower bound for a graph that I know of, because Hoffman managed to prove that here you can increase the lower bound by not just one, by more, and then it still wasn't enough to get the value of this graph. So yeah, so simple graphs you cannot find this thing. So okay, let me see. What do I want to show you? Okay. All right. So I'll stop here. I have about 15 minutes for the first part, or how much? 15 minutes. So I'll change the topics again to something else. So if you have any questions about this addressing, let me know. If not, we'll move on. I'll erase this. Okay. Okay, so let me see. Okay, so let me tell you something about, so I don't know if I'll finish it now or I'll finish it, I'll definitely finish it in the second part. So let me give you an example of a recent application of eigenvalues for a different problem, which was, for which the solution was given in a tweet. So the solution of the proof of this result was summarized not by the author, by somebody else, was summarized in a tweet. Now we're going to do the longer version of a tweet over an hour or something to tell you about this. So this is about what is called sensitivity conjecture. So sensitivity conjecture is a conjecture in computer science. If you look online, you'll find many descriptions of it. In computer science, people study these Boolean functions and so on. So functions that depend on many variables, and they want to see how the function changes if you change one of the variables and so on. Or that's called sensitivity of the function. Or they want to see how the function changes when you change blocks of variables. That's called block sensitivity. And there was some relations from the 80s between these sensitivity measures, and then there was some conjecture about the inequality holding on the other side, and that has been open for many years. And people have tried to they've actually reinterpreted the conjecture in terms of a graph theory question. And the question in terms of graph theory is the following. So let's say for n greater or equal to 1, Qn denotes the n-dimensional cube. So what is this? We talked about it before. The vertices are binary words over 0, 1 of length n, and the edges you have x1 blah blah xn. So let me write it like this: x1 xn adjacent to y1 yn, if and only if there exists exactly one j from 1 to n where xj is not equal to yj. So the two words differ in exactly one position. So that's the cube. So, you know, let's say start from n equals 1. This is 0, 1, and then again you can construct it like this. If you want a recursive construction, you can take the cube here. We talked about this earlier. You make 2 copies here, 2 copies of this, and you put a 0 to the end of one, and you put a 1 to the end of the other, and you join them by a perfect match. And then you continue. So you can do something like this here. So you have here 1, 0, 1, 1, 0, 1, 0, 0, and you can take another copy here. 1, 1, 1, 0, 0, 1, 0, 0. You add you know, a perfect matching here, and then you put a 0 to the end here. You put a 0 to the end here. 1, 1. Thank you. 1. Now you can do this. So the Hamming graphs that I mentioned a bit earlier, if I take, instead of the alphabet to be 0, 1 to be an arbitrary alphabet with more than 2 elements, that's going to be called the Hamming graph. So this is the cube is a special case of a Hamming graph. Okay. And the cube, you know that it's a bipartite graph. What are the bipartition, the color classes? Even and odd weights. So the ones that have even number of ones you put on one side, the ones that have, you know, so the Qn, you have here 2n minus 1, you have here 2n minus 1. These are even and these are odd. Okay? So this problem about, so the sensitivity conjecture is the following. Let gamma be an induced subgraph of Qn with more than half of vertices, 2n minus 1 plus 1 vertices. So this is just so that you don't just take, if you have 2n minus 1, you could just take this part, okay? Then the maximum degree of gamma is greater or equal than square root of n. So what this says is, if you take more than half of the vertices in the graph, you're guaranteed that among those vertices, one of them will be adjacent to at least square root of n of the others. I mean, for small values, maybe that's not going to impress you that much, because here, what does it say? If n equals 2, if I take 3 vertices, if I take the subgraph induced by it, the maximum degree of it will be at least square root of 2, but it's integer, so it will be at least 2. So if I take 3 vertices, no matter how I take them, I will take a path of 3 vertices, so I will have a vertex of degree 2. Okay, so here it starts to get a little. If I take any 5 vertices here, you know, A choose 5, A choose 3, A choose 3. 8 times 7, 56. Okay. Any subgraph with 5 vertices, the minimum degree will be at least square root of 3. So if it's at least square root of 3, at least, because you bump to the next integer. 3. 2? Square root of 3? Oh yeah, it's 1.7. Yeah, I was getting ahead of myself. I'm not going to draw this one, but yeah. Okay, so this is what Huang proved. Hao Huang. I forget which summary was, but look up online and you can see the paper on arXiv when he posted. And this was like a big news because pretty much everybody could follow the proof, understand what he was doing, and everybody was mesmerized that nobody has seen this before. Of course, you know, you look at it, well, you know, hindsight is 20/20. When you see some, you know, and then many people try to do the same thing for other graphs. Okay, so I'll give you the idea of the proof. So you have Qn, the graph here, and you take a subgraph here. Let's call it gamma. Okay. Now, the thing about graphs, we had in one of the earlier exercises, what is the lower bound for maximum degree in terms of spectral things? Here, like in this statement, there's nothing about spectrum, nothing about eigenvalues. But we know before that maximum degree beats every eigenvalue, so it beats the largest eigenvalue. So it beats lambda 1 of gamma. Okay. Now you could try to do this, but the problem is that the eigenvalues of the cube, which we haven't discussed, but I'll talk about them maybe in a little bit. So let's do something aside here, eigenvalues of Qn. Okay, n equals 1. This is Q1, 1 minus 1. N equals 2. Here's a quick trick that you can use to get from one eigenvalue to the other. Because you have this procedure of taking copies and doing this, you get the eigenvalues from before. If you had here lambda, then you're going to get lambda plus minus 1. Because you can take the same eigenvector from here, put it here. You can put it here, so it's going to give you lambda plus 1. Or you can take the same eigenvector from here, put it here, put the negative of it here, and it's going to give you lambda minus 1. So 1 minus 1, 2, 0, minus 1, 0, minus 2. I'll show you tomorrow a different way, but you can calculate this in a different way using characters. Okay? N equals 3, it's going to be 3, 1. You're going to have 1 with multiplicity 3, minus 1 multiplicity 3, 3 multiplicity 1. And it goes like this, okay? So the problem is if you try to do here because this is induced, if you try to do some Cauchy interlacing about the largest eigenvalue, the bound that you will get for lambda 1 here is not going to be good enough for you to get square root of n. Okay? So what Huang did, used a signed adjacency matrix. So he took the adjacency matrix of the Q, and from it he came up with another adjacency matrix. Let me call it Bn, which is symmetric, and he has eigenvalues, has entries 0, 1, and minus 1. So he just here in this adjacency matrix you just have zeros and ones. So he just changed some entries in he did it recursively, but you can do it in other ways. So he showed that for the cube with n dimensions, you can find a signing, so you can change some of the 1 entries to minus 1s, such that this matrix Bn has a very nice spectrum. The eigenvalues here will be square root of n with multiplicity 2 to the n minus 1, and this one will be minus square root of n with multiplicity 2 to the n minus 1. Which is kind of like, okay, there's a square root of n, so maybe there's something. Here, for the usual adjacency matrix, the eigenvalues of the cube will be something like this, n with multiplicity 1, n minus 2 with multiplicity, I think, n choose 1, n minus 4 with multiplicity n choose 2. So they go like this, okay? So they're minus n with multiplicity 1 and so on. So they go like this. But here, he showed there is a way So how did he do it? He did it, so the idea was to think about it, this recursive thing about Qn. What you have is you have Qn minus 1, you have Qn minus 1. So when I'm looking at the usual adjacency matrix of Qn, you can think of it as what? It's kind of like a block matrix. I have here adjacency matrix of Qn minus 1. I have here adjacency matrix of, no, the other way around. I have here adjacency matrix of Qn minus 1. I have here adjacency matrix of Qn minus 1. And what do I have here in these blocks? Identity. Identity for 2n minus 1, identity of 2n minus 1. Okay? Now what he did the same thing. He used this to create this sign adjacency matrix. So he started, okay, B1 is the one for the first cube. It's identity I2. Nothing fancy there. Okay? Now B2, so in general, let's give you Bn. You look at this picture here, you will do almost the same thing. You do Bn minus 1 here. You put the same thing I2n minus 1, I2n minus 1. And then here you put minus Bn minus 1. And then you can, if you want, you can do induction. I think that's what he did, that if Bn minus 1 has eigenvalues square root of n minus 1 with these multiplicities, then Bn will have these eigenvalues. Okay? So how much time am I finished? Is it 3:30? Did I finish? I forgot.
2 more minutes.
2 more minutes, okay. All right, so I'll leave it here for now. Obviously, exercise number 30-something, 31, is to figure out that the eigenvalues of Bn are this. Obviously, the easy way is to go find his paper and see how he, but you could, if I told you now how to do it, you can do it yourself. Just square the matrix Bn and see what happens. Because again, if you think about it, Bn having these two eigenvalues is going to end up equivalent with Bn squared equals I to the 2n. And if you assume that this is the case for Bn minus 1, see what happens if you square Bn and multiply these things around. Okay? So you can do that. Okay, so let's take a break now.
B1, maybe you have to take 0, 1, 1, 0.
Yeah, you're right. Yeah, you're correct. B1, it's the adjacency, yeah, it's the usual adjacency matrix of, very good. It's the usual adjacency matrix of Q1. You're correct. Yeah, 0, 1, 0. Thank you. Yeah. Okay, because that's 1 minus 1. Okay. Okay, we'll take